Howdy, Calc BC. Welcome back. Here to take a little bit of a detour, I guess. It's going to feel like it anyway, a little bit. What we're doing next here, after we move on from infinite series, is we start examining some of the work that was done by a couple of Newton's contemporaries. A guy named Brooks Taylor and another guy named Colin Maclaurin. And there's actually another mathematician named Lagrange in there as well. So, yeah, these guys were all living around the same time as Newton. They were working on something that kind of related to Newton's work, and so they started working with complicated functions, or at least transcendental functions that were difficult for them at the time, because they didn't even have slide rules for computing power. So it was pretty difficult for them to work with a lot of these curved functions. But the functions that they did know pretty well were polynomials. And so they started looking at if we could take a complex function, transcendental function, exponential function, logarithm function, and model it with a polynomial function, at least close to a point where the two functions met up. And we've actually already done this. We did this with first degree polynomials way back last year in Calc BC, or sorry, AB. Yeah, it was tangent line questions. The tangent line to a curve is a good approximation to the curve when you stick close to the point of tangency. And so what Taylor and Maclaurin were kind of working on at the same time was, well, okay, so if a linear function is good, maybe a higher order polynomial is going to be better. And they wanted to see what would happen. So I'm going to go back to Calc AB for a moment and take a look at a function. And we're going to construct a polynomial to kind of model this function. So my function I'm going to start off today with is a favorite of everyone's, I think. Because it's e to the x, and everybody just loves e to the x, right? Primarily because it's got the simplest derivative there is. So we're going to look at the function e to the x, and I'm going to write a tangent line equation. So that's a first degree polynomial, aka line, and nomial to approximate f of x. There we go. At, excuse me, the point 0, 1. So obviously, if you put in 0, you get, f of 0 is e to the 0, which is, of course, 1. And so we know that's the point that we want to write the tangent line equation. And so we're going to need a slope. And the way we find slope, of course, is to find a derivative. So let's take a look. F prime of x is, well, you got it, e to the x. And so the slope at the point when x is 0 is also 1. So thinking about my function then, I know f of 0 is 1. So I want to write a polynomial function, a first degree polynomial. So this is going to be some new notation. P sub 1 is kind of, we're going to use that for a first degree polynomial. P sub 2 is going to be a second degree, third degree would be P sub 3, and so on. So you get the idea. But really, it's just a tangent line function, right? What's that P sub P1 of x look like? Well, we know, right? We could say, well, okay, look, we know it's y equals mx plus b, right? We know that m is 1. Sorry. And b there. And we know it goes to the point, 0, 1. So 1 equals 0 plus b. So b is 1. So what I get is 1 plus x as my tangent line, or in the language we're going to start using, a first degree polynomial approximation to the function e to the x. And I've actually got that ready to graph for you on my Desmos graphing calculator here. So here's my e to the x function here in red. And when I click on the polynomial 1 plus x, look at that. If you stay pretty close to where the point of tangency is, that point 0, 1, the blue line, kind of matches up with the red curve for a little while. And that was the idea, right? That the tangent line was a pretty good approximation as long as you stuck close to x equals 0. So what Taylor and Maclaurin did was they said, well, if the linear one's good, what about a quadratic one? And so what they did is they said, okay, well, if we use the similar kind of reasoning, then, you know, if we know we want a second degree polynomial, okay, so we want P2 of x to be like, you know, ax squared plus bx plus c, okay, and we also know, right, we want P2 of 0 to equal 1, right? It's got to go through the same point, 0, 1. We want that same point of tangency. We also know we want the first derivatives to match up, right? So P2 prime of 0 needs to equal f prime as 0. And we'd like the second derivative of 0 to match up with f of 0 and f double prime of 0. And so, yeah, so we could go through and use these three conditions to solve for a, b, and c. You know, for example, we know if P2 of 0 is 1, that's a times 0 plus b times 0 plus c. So there we go. Obviously, c is 1. We know f prime equals of 0 equals 1. We know P2, you know, its derivative would be 2ax plus b, right? And if, you know, if we go through the point 0, 1, right, well, then you can solve for b and get b is equal to 1, right? Put in the 0 in here and you get 2 times 0 plus b equals 1. Oops, 1. And f double prime has to equal p double prime is 0. Well, that's 1. And what's f double prime? Well, it's 2a, right? 2a has got to equal 1. So a is going to be 1/2. And so what I end up with here for P2 of x, I'm going to write it in backwards order, and that'll make more sense later, is 1 plus x plus 1/2 x squared. And for you savvy folks who are cool with Desmos, you probably saw that I was already going to graph that one because I pre-planned that out. And so I'm going to go back to my Desmos and look what happens when I graph that function in place of the linear function. So let's go back. I'm going to turn off the linear approximation. Well, maybe I'm going to, there we go. And I'm going to turn on the quadratic. And what I want you to see is that the green parabola matches up with the red curve for a larger interval. Okay, if I put the blue one back on, you'll see the blue one starts to diverge a lot earlier, diverge away from the red line a lot sooner than the green one. The green one makes it a little bit farther. Okay. Now I've taken the liberty to go ahead and find the third degree polynomial. I will spare you the solution for that because it does involve a 4-variable system. But here we go, and look at this purple one. I mean, as we go towards the top, it's barely it's indiscernible from the red line up here. So we can get a lot farther away from that point where I wrote the equation, and still have a really good match. So I mean, and I'll put all of them on here so you can kind of see the comparison here. So the blue line, well, turns out, yeah, linear approximation's good, but you really do have to stick pretty close. You know, I mean, once we get out past about here and about here, the blue line starts to visibly diverge from the red graph. Green parabola, well, you get a little bit further, right? I mean, if I go out to, oh, I don't know, about here, maybe back to about here, so you can start to see the visual separation come in pretty good. But look how far out we can go on the purple graph. I mean, you know, I'm all the way up here at the top, and we're still very close. Down here on the lower side, yeah, we get some separation around here. But you can see that I add a degree to the polynomial, I get a much larger interval where the red curve and the, well, whatever color you want to choose, their polynomial graph match up. That was the idea that Taylor and Colin Maclaurin were working with. So what they did was they developed these things, and we call them literally Taylor polynomials or Maclaurin polynomials. Now, a quick word, the point where I started the whole thing, Now, let me get a different color that's going to match up. Let me pink right here. Okay, that's called the center, okay, of our polynomial. And the reason it's not just the point of tangency is because you know, tangents are for lines, right? You have tangent lines, okay? And we didn't want to be thinking too much linear now. We wanted to be thinking about polynomial. It's also going to be the center of something later called an interval of convergence, and you can imagine convergence divergence comes in a little bit later. So it's the center of an interval as well. And so I think getting used to calling that the center and not the point of tangency will be good for us. We'll want to develop that sort of vocabulary here as we go along. So let's go back to our whiteboard here. And oops, I gotta get the pointer, not the pink pen. There we go. And, oh, I went back to sharing the same thing. There we go, whiteboard. And so let's see what Taylor and Maclaurin came up with. Now, the Taylor polynomial is a more general case, and so let's put that one on the board first, and then we'll take a look at what Colin Maclaurin was coming up with later. So a Taylor polynomial. All right. So again, linear works, okay, but we wanted to know what would happen if we got a higher order polynomial. So if the function f that we have, okay, if f has n derivatives. I don't know if you can hear my dog barking in the background. I don't know what's going on outside, but she's very very angry at whatever it is. It's probably a bird, to be honest. She does a lot like, well, she's kind of a bird dog, and so she likes to chase them. Okay, so if it has n derivatives at the point C, now there's that center point. Okay, that's the center of our polynomial. See, the polynomial, okay, or sorry, then the polynomial okay, so here we go. P sub n of x. Okay, it goes like this: f of c plus f prime at c times x minus c to the first plus f double prime at c times x minus c squared over 2, okay, plus f triple prime at c over 3 factorial times x minus c quantity cubed. Okay, now for higher order derivatives, right, we don't keep going with primes, right? So dot, 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 plus the nth derivative. Okay, we put the higher order derivatives in parentheses up above the f right there. At c over n factorial times x minus c to the n. Okay, that polynomial is called the nth Taylor polynomial. There we go. That's how you find a Taylor polynomial. You can see why it kept going with the derivatives. Now, I know I put a 2 in the bottom here. You could write it to remember it. You could write it as 2 factorial. 2 factorial is 2. But I think for continuity's sake, it's kind of nice to have the factorial down there. It's up to you. But that's how we come up with what we call the Taylor polynomial. Any function that has n derivatives at point C, we can approximate using this polynomial here. Now, if the center happens to be 0, okay, so if C equals 0, okay, then P sub n of x is called a Maclaurin polynomial. And nth Maclaurin polynomial. Okay, and so instead of C, right, everything's done at 0. So much like the one we did for e to the x when I started, that was actually a Maclaurin polynomial. And so p sub n of x, you just put in 0 everywhere you have a c. So we have f of 0, f prime of 0 times x, f double prime at 0 times x squared over 2 factorial, f triple prime at 0 over 3 factorial times x cubed, and so on, until we have that nth derivative at 0 over n factorial times x to the nth power. And so, yeah, so basically Maclaurin got his name. He was doing the same work at the same time. Not really associated with Brooks Taylor, but they were similar in terms of they were working at the same time, but not connected. So they did the same kind of thing. But Taylor gets the general one, and then Maclaurin get the one that we center it at 0. So that's how we come up with our polynomial. It's an approximation, of course. Okay, as we saw, in the graph, eventually they do diverge from one another. But the nice thing about the polynomial is it's a polynomial. They're so nice and well behaved. And remember, these guys. So this was like the early 18th century. So Newton was born in the late 17th century. He died in 1727. So this was at the time when we didn't have a lot of different things for computing. They didn't have slide rules, they didn't have calculators, they didn't have any of that stuff. Taylor was actually very young. He was only 46 when he died. He outlived Newton by a couple of years, but not very far. And Maclaurin lived a little bit longer. He died in 1746, so he outlived Newton by a few years. But yeah, so these guys were all contemporaries of one another. They're all working together. And it was kind of interesting because they are all, but they were in different fields. Kind of, Newton was very much a physicist. Taylor was developing his polynomials, Maclaurin was developing his polynomials, and they all ended up kind of landing in the same spot, which is pretty cool. Okay, so if I go back to my e to the x example, okay, let's go back to that. You can kind of see then, how I was able to get P3 pretty easily, because I said, well, okay, I wanted P3. If I wanted the nth Maclaurin polynomial, right, I would have my ones that I already know, 1x plus 1/2 x squared, and then you saw on the Desmos it was 1/6 x cubed, on so forth. And so we'd end up with, that's supposed to be a plus sign, but it doesn't look very much like a plus sign. There we go. I'd have 1 over n factorial times x to the nth power. And so wherever I wanted to stop that polynomial, then what would happen is I would keep adding on terms that fit that pattern, and I would eventually have a nice polynomial that would approximate e to the x. And obviously, as I go higher in degree, I have a better polynomial, right? It matches for longer. Further we go from the center of the polynomial, we can still have a pretty good agreement between our function and our polynomial. And so let's try it with a different function. I'm gonna try a different polynomial here. I'm gonna actually try a Taylor polynomial as well. So I don't want to just do Maclaurin polynomials. So this time, my function f of x here is going to be a new function. It's going to be natural log of x. And you're probably already thinking, hey, natural log of x has a problem at 0, right? Yeah, it does. It's undefined at 0. It's, as x goes to 0, it goes to negative infinity. So there really is no Maclaurin polynomial here. So I want to find a Taylor polynomial. And actually, the book, this is example 4. They have like find P0, P1, P2, P3, P4. I'm just going to say, let's just find, P3 of x and P4 of x. Okay, just to kind of highlight how we do this. But what's our center, right? Well, I'm going to choose a simple center. I'm going to choose 1. Now, the reason I chose 1 is, well, obviously, f of 1 is 0. So, yeah, if you put in 1, natural log of 1, you get 0. So this makes our life a little easier when we go to plug some things in and start finding our coefficients. So if I want P3, I know I'm going to need f prime of x. I'm going to need f double prime of x. And I'm going to need f triple prime of x. Come on. There we go. And you know what, while I'm here, let's get the fourth degree or fourth derivative. So I can write the fourth degree one later. Okay, so what is f prime of x? Well, obviously, natural log derivative is 1 over x. So what's the second derivative? Well, negative 1 over x squared. What's the third derivative? Yeah, 2 over x cubed. And fourth derivative is negative 6 over x to the fourth. So now we have our different derivatives. Let's plug in and see what this is at each of the, when we put in the center here. So what's f prime at 1? Well, it's 1. What's f double prime at 1? Well, negative 1 over 1. Negative 1. What's f triple prime at 1? Well, it's 2 over 1, so it's 2. And what's f fourth derivative at 1? Well, obviously that's negative 6. So there's the coefficients that we're going to use as part of our polynomial. And now we just need to put them together into our polynomial. So I'm going to write, start off with first P3 of x here. And I know I'm going to start with f, the function evaluated at the center, 1. And then I'm going to add f prime at 1 times x minus c, which is 1 to the first power. And then I'm going to have f double prime at 1 over 2 factorial times x minus 1 squared. And lastly, I'm going to have f triple prime at 1 over 3 factorial times, oh, I'm going to try and squeeze that in there. Oh, that was terrible, but you get the idea. And as I said earlier, f of 1 is 0, right? We saw that right here. So my first term is 0. So I'm just going to go straight to the next one. What's f prime at 1? It's 1 times x minus 1 plus f double prime at 1. Well, that's negative 1 over 2 factorial, which is 2 times x minus 1 squared. Okay, plus f triple prime. Well, that's 2 over 3 factorial. Now, 3 factorial is actually 6. So I'm going to reduce that down. And I'm going to get x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 quantity cubed. And there is our third degree Taylor polynomial for natural log of x centered at the point 1, 0. Okay, and for P4, let's get a different color of pen here. Let's go blue. So P4 of x, I'm just going to take that P3 and I'm just going to add on the last term that I know is the fourth derivative at 1 over 4 factorial times x minus 1 to the fourth. Now the fourth derivative is negative 6. And remember, 4 factorial is 4 times 3 times 2 times 1. Well, that's 24. And so you get negative 6 over 24, you get negative 1/4. So we get x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed. Oh, I forgot to write the cubed. And minus 1/6 x minus 1 to the fourth. And some of you might be looking at it going, that seems to alternate signs as it goes along there. I wonder if that's an alternating series of some kind. And you'd be right. That's for later. Yeah, that's for later when we get a little bit further along. So that's how we go about writing a Taylor polynomial, a fourth degree Taylor polynomial and a third degree Taylor polynomial. And now you could do second degree or first degree, all those fun things. And we could keep going if we wanted to do a fifth degree Taylor polynomial, we can. You probably could see what the pattern is, right? I mean, is it a quinkydink that it went, 1, 3, 6? Oh, probably not, right? So the next one will be what, 1/20th? And so you get the idea. So like all things here, though, when we're doing this, we're not using the exact function, right? we're writing a polynomial that's going to approximate that function, okay? Which means there's probably an error, right? And kind of like when we did alternating series, right? We might be interested to know just how bad is it? Like, how close is the error, right? And that is a whole nother part of section 5 or 8.7, 5.7. Sorry, I'm doing chapter 5 of the AB kids and already made a video for them. So 8.7, there is a remainder theorem for Taylor polynomials. Okay, it's actually called Taylor's theorem. So in Taylor's theorem, okay, oops, that's an O. What he was doing was saying, okay, this is all great. This is awesome. I love having this polynomial. So much easier for me to work with than some nasty function like e to the x natural log of x, sine, cosine, whatever. Because again, working without a calculator, really tough. So what he wanted though was say, well, okay, it's good, but how good? Like how far off is this thing going to be? Okay, and he actually developed a way to tell. Now, this is where Lagrange comes in, because this French mathematician Lagrange was doing this same kind of work, of course, because everybody was doing this work at that time. And so sometimes this, what we're going to do here, it's Taylor's theorem, according to Dr. Larson. When we get to how do we find the error, the remainder, sometimes it's called the Lagrange error bound. And so it kind of depends on who your textbook author is a little bit. Calculus is still, I mean, it's old, but it's not as old as like algebra. And so we still have some maybe some disagreements over who gets credit sometimes. It's kind of like Leibniz, Newton, all that stuff. So Taylor's theorem basically says, okay, so our function f now, if f has n plus 1 derivatives, okay, on this interval, we're going to call it I, that contains our center. Okay, excuse me. So we have n plus 1 derivatives. Okay, that's a big deal right there. Okay, so we're not going just to the nth derivative now. You can imagine we're going to need the n plus 1 derivative. And on this interval I, and it contains c, then, okay, for each x that's in the interval I, okay, that the lowercase epsilon means is a member of, right, is in the set I. Okay, then for each I, there exists a z. Now I'll try to clear up what z is doing here in a minute. That's between x and the center, okay, such that, okay, so so we're saying, look, we're approximating our function with this polynomial, right? Because it's a Taylor theorem, so it's going to involve this polynomial, and we're looking on an interval around the center, right? Remember when I was showing you those intervals, like where the function was lining up pretty well with the red graph, and then it got further away and it didn't line up so great? Okay, so imagine those intervals. That's again why I said C is the center, right? Because it's the center of that interval usually. Then every time we pick a different x value in that interval, okay, there exists a z in between the two, between the center and that x coordinate, such that, okay, f of x equals f of c plus f prime of c x minus c plus f double prime of c over 2 factorial x minus c squared. Okay, you see what I'm doing here? I'm just writing out the Taylor polynomial. X minus c to the nth plus some remainder. Okay, so what we're saying is f of x, not the polynomial, the actual function, is equal to all of this, which is the polynomial. That's the nth degree Taylor polynomial, right? Plus some remainder. Okay, so let me pull up my Desmos again here. What I'm saying is, if I move this a little bit, okay, where's my pointer tool here? There we go. Okay, and if I focus in on just the green one for right now, so let me get the other ones off there. Here's C is down here. Let me draw that and highlight that here for you. C is down here. If I go over some amount here, okay, then what we're saying is there's a bit of remainder here. That's the remainder of the second degree polynomial evaluated at whatever x value this is. So this looks like 0.5, 0.6, 0.7, 0.8, 0.9. Yeah, so this would be like 0.7. Okay, and so there's some remainder here. So the actual function is the polynomial plus that little distance at 0.7. That's what we're saying. Okay, that's all we're saying right now. Okay, but what Taylor goes on to do, he says the polynomial's remainder, he defines it, r sub n of x is equal to the n plus 1th derivative at z over n plus 1 factorial times x minus c to the n plus 1 power. And that is the beauty of Taylor's theorem. He allows us to have a way to quantify that remainder by saying, look, it's the n plus 1th derivative at this value z that's somewhere between x and c, okay, over n plus 1 factorial times x minus c to the n plus 1 power. If I go back, I could show you that, when we went from squared to cubed, right? Well, then that's the next derivative, right? Okay, and so you could find the remainder that way. The problem is that darn z term again, right? We don't know what z is. In fact, if we knew what z was exactly, there'd be no need to approximate the polynomial, the function with this polynomial anyway. We'd know exactly what the remainder was. There'd be no more approximating. We could find exact values. Okay, so that's where Lagrange comes in. They said, well, okay, that's all well and good, but in reality, okay, I don't know what z is. But what I can tell you, if I rewrite that term just a little bit, okay, if I move the x minus c into the numerator, okay, and I put the if I put the derivative out here and I say, well, find the maximum value of the n plus 1th term evaluated at z. Oh, absolute value signs. There we go. Then I can at least give you an upper bound, an upper limit for how bad the approximation is going to be. And that's really what we do with Taylor's theorem. Okay, we don't ever find the exact remainder, okay, unless you have a calculator and then you can find exactly the function value at that point, evaluate the polynomial at that point, you can subtract them, and then you say, oh, look, here's the exact remainder. Most of the time, though, we don't really care so much about it. Okay, what we really want to know is just, okay, what's worst case scenario for this round off error that we might be experiencing right now. Okay, and that's where this can really help us. Now, when it comes to figuring this bit out right here, Okay, it's the maximum value of the n+1th derivative at z. The thing to remember, okay, is that z is in between x and c. Okay. Or, okay, so sometimes it's just a matter of saying, okay, here's the center, here's how far out we are going in the interval, right? And what's the maximum value of the function on that interval? Okay, sometimes it's easier because the function has like a global max, and so you could just be like, when you do the n+1 derivative, you're like, well, you know, if it's sine or cosine, right? The global max of sine and cosine doesn't matter where you are; it's always 1, so you can multiply by 1. Okay, the example that they have for us, example number 8 on page 612, is actually, let's write a polynomial for sine of x, the third degree Maclaurin polynomial for sine of x. Third degree Maclaurin for f of x equals sine of x, and then find the error bound when using, oops, looks like a weird b, I meant to make a p, 3 of x to approximate sine of 0.1. Okay, that's what they're, I think it's 0.1. Yeah, sine of 0.1. Okay, so first things first, the third degree Maclaurin for sine of x. Now, where's the center? Okay, remember, a Maclaurin polynomial is centered at 0, and you have to remember that. Okay, when you get the AP exam, free response problem number 6 will have something to do with Taylor and or Maclaurin polynomials. They don't say centered at 0. If they want it centered at 0, they're going to say Maclaurin polynomial. They expect you know that means it's centered at 0. So let's start by finding the derivatives. F prime, F double prime, and F triple prime. Well, F prime of x, that's nice. That's sine of x. F double prime, oh my gosh, sine of x. We're starting with sine of x. I'm so sorry, guys. It's been a long day already. It's cosine of x, though, of course. Then we get negative sine of x. And F triple prime is then negative cosine of x. Okay, jeez. Sorry about that. Okay, so now let's go back to the fact that we're talking about a Maclaurin polynomial. So it means we're centered at 0. So P3 of x will be sine of 0, okay, plus cosine of 0 times x, plus negative sine of 0 times x squared over 2 plus negative cosine of 0 over 3 factorial x cubed. And sure enough, sine of 0 is 0, cosine of 0 is 1, sine of 0 is 0, cosine of 0 then negative. And we can see that our third degree Taylor polynomial, Maclaurin polynomial, P3 would be x minus 1 over 3 factorial x cubed. Okay, but I said, what's the error bound when using this polynomial to approximate sine of 0.1? So what is the fourth derivative, right? Because remember, it has to have n+1 derivatives. Well, the derivative of negative cosine is sine. So I know the absolute value of this remainder R3 of x is less than or equal to, well, x to the 4th over 4 factorial times the maximum value of sine of z. Okay. Well, the maximum value for sine of anything is 1. So this is x to the 4th, oops, there we go, over 4 factorial. And then notice I said we're going to use it to approximate the sine at 0.1. Okay, so 0.1 to the 4th over 24. Okay, well, 0.1 to the 4th is 0.0001. So 0.0001 over 24, which is really small. How many zeros is that? 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5. There we go. So it turns out that a Maclaurin polynomial to approximate sine, as long as you're at 0.1, is actually really good. Tenths, hundreds, thousands, 10,000, 100. That's 4 millionths. That's really close. Yeah, so you don't need a whole lot of terms. Again, stay close to the center of your polynomial. Sine of 0.1 is pretty close to sine of 0, right? Where we centered it. Okay, so yeah, we're going to be pretty close when we make the Maclaurin polynomial, as long as we stay close. If this were to go further away, obviously x would increase, and notice that would increase the error bound. Okay, the error bound is tied to two things. Well, you know, the derivative, of course, but it's, you know, what determines the accuracy of course, the derivative, and then the maximum value of that function. But then you plug the x coordinate in, and that shows you how far off you could be. And that's pretty accurate. So yeah, these guys were pretty darn accurate when it came to getting these polynomials put in there. So anyway, that is Taylor and Maclaurin polynomials. That is the error bound for a Taylor polynomial. And we will be working with Taylor and Maclaurin a lot in the second half of chapter 8. So hopefully these polynomials went fairly smoothly for you. We're going to get a lot of time to work with them here in class today. So, or in class when I see you. It's Wednesday making the video right now, but when I see you in class tomorrow. All right. Thanks so much, guys. I will see you in class.